So in this session I will get into the beginnings of proof that the class of regular languages is closed under the operation of concatenation. That was theorem 1.26? Yeah, 1.26. But as I said a bit earlier, we will get stuck. We will reach a point where we can't go any further, and that will motivate quite a long digression into a new topic, a powerful new topic called Nondeterminism. It's a whole different style of computing. Up to now, it's been rather implicit, unconscious almost, that the style of computing we've been doing up to this point is deterministic, and I'll explain what deterministic computation is. I'll also explain in this session what non-deterministic computation is, and we will be on this theme of non-determinism for quite some sessions. It's a major topic, so be prepared for that. All right. Well, so before we get stuck, we have to reach a point to become stuck. So how to get there? Well, how do you think you would go about starting to prove that closure under concatenation? Well, maybe again, use the two machines, M1 and M2, and have machine M1. That's concatenation, right? So you're talking about all possible concatenated xy's, where x is some what is x and y? X is some string from alphabet A1, and y is some string from input string from alphabet A2. Okay, so one idea might be to again use two machines, simulate in the similar way that you did for the previous theorem, 1.25. Have machine M1 look at the string x. Right? So you're trying to simulate M1 and M2 in such a way that your machine M, whose job it is to recognize concatenated strings xy as they come in. So you'll have machine M1. This is the idea, the core of your proof, 1.26. Have machine M1 look at the x part of the concatenated string, and have machine M2 have a look, detect the y part of the concatenated string xy. And if x1 detects, accepts the x part, and if machine M2 accepts the y part, detects the y, then your machine M will accept. Okay, that's the sort of broad idea. There's a problem though with it, and that is how on earth do you know where the division line is? Like, where does x end and where does y start? So you don't know that. So you got to, that's a major headache, and that just blocks everything. All right. So problem. You don't know where to break the input string. You don't know where the first part ends and the second part begins. Where does x end and where does y start? That's the problem. Because it's a major headache. All right. So to get around to solve this problem, and it can be done, you need a major new concept, a new topic. So it's like a whole new section, right? So 1.2. So the stuff we've been doing in this chapter before it was a whole section, 1.1. So now we're into a whole new section, and this section is labelled Nondeterminism. So I need to explain to you what determinism means, and then by contrast what non-determinism is, and then make clear what some of the differences are between these two styles of computing, deterministic computation and non-deterministic computation. Right? Now, before we get into the definitions, a little bit of general comment. So non-determinism, it had a major impact on the theory of computation. It really helped things. For example, we could solve problems like this. Because now we're stuck, but thanks to the introduction of this new concept, style of thinking, it had a major impact on the theory. Right? Okay, so what is determinism? Now, right here, all through this course so far, we're unconsciously, implicitly, been using a deterministic style of computation. What does that mean? Well, determinism, speaking broadly, it means that, for example, when you're trying to calculate the next state, so say with your transition function, your delta, and you're in a current state, and you're looking at the current input symbol, then your transition function will calculate for you the next state. Okay? Now, we haven't thought about the probability of getting that next state, right? Because we've just assumed unconsciously, I guess, that that transition function will give us, with certainty, and that's the critical concept, right? With probability 100%, with no doubt, okay? We will definitely be in a given next state, right? So the next state is determined without any doubt. It's determined with certainty, with probability 100%. That is determinism, okay? When there's no uncertainty. Now, in determinism, the essential difference, non-determinism, essential difference from that relative to determinism is that when you come to calculate the next state, you might get more than one, or even zero. So the next state is not definite. It's not assured. It's not certain that it'll be a particular state. Right? You may have several next states, okay, with a certain probability. There might, the next state might be state 1, and also it might be state 2. So in other words, the number for a given current state and a given symbol that's being read in the input stream, then if you're using non-deterministic computing, there may be more than one next state. Okay? That's the difference. That's the essential difference. Now, there are other differences, but that's sort of the main one. Okay? So summarising a little bit.